Okay, we're looking at homework M6C2 test electric fields, particularly question number 10, which reads, the illustration below shows a horizontal beam of electrons moving in a vacuum. The electrons pass through a hole in the center of a metal plate A. At B is a metal grid through which the electrons can pass. At C is a further metal sheet. The three vertical conductors are maintained at voltages of plus 600 volts at A, 0 volts at B, and plus 1200 volts at C. The distance from plate A to grid B is 40 millimeters. Calculate the minimum speed that an electron in the beam must have at the hole in A to reach grid B. How fast must the electrons be going here in order to make it through this gap? They'll be slowed down until they hit this part. How fast do they need to be going to make it to this grid? So this is almost like a bowling uphill type question. You know, how fast would I need to bowl a ball to get it up this slope? You know, effectively this potential difference of plus 600 volts to 0 volts for a negatively charged electron, this would be like going uphill. So if it were a bowling ball going uphill, you would do a half mv squared and convert that into mgh, and therefore the distance that the distance from here to here would be completely irrelevant in that circumstance. Consequently, this piece of information here about the distance between A and B being 40 millimeters, that's just a red herring. So let's start with the defining equation for the volt, and we'll leave behind the diagram as well. The volt is the amount of energy carried per unit charge. We can rearrange that to make energy the subject. Energy is charge times voltage, potential difference. We know that the charge carrier in this case is an electron, so the charge is going to be the electronic charge, 1.6 times 10 to the minus 19 coulombs. And we can substitute that in to get the electric potential energy, the energy associated with this situation, equals the electronic charge times the potential difference between plus 600 and 0, which is going to be 600. So we're going to use that expression for energy and join it onto the expression for kinetic energy, half mv squared. Putting these two together, we end up with electric potential energy equals a half mv squared. So if we move that to the top of the page to give us some working space, all we need to do now is rearrange this for velocity. Now I've got lowercase v for velocity, uppercase V for voltage or potential difference. Important you don't get those two mixed up. So rearranging for little v, velocity, we end up with the square root of 2ev divided by m. Okay, so we've got 2 times the electronic charge times the potential difference, which is going to be 600, divided by the mass of an electron. So the figures that we need there are the electronic charge, 1.6 times 10 to the minus 19 coulombs. The potential difference is trying to overcome, 600 volts from the diagram. And the mass of an electron is a number that you should know, 1.9 times 10 to the minus 31 kilograms. Plug those numbers into that equation, and you should get an answer that is less than the speed of light.